Welcome to this lecture series in real analysis. In this lecture, we will prove a key theorem about power series and their derivatives, and let us recall some relevant things. So first of all, we will need that this limit is equal to 1, and we have seen this many times. So I'm not going to recall the proof of it, but if you don't recall the proof, or if you're unsure about it, you can just take this as an exercise. A simple consequence of the previous one, or another exercise if you will, is that this limit is also 1. Of course, changing n to n plus 1 is not going to make much of a difference once you take nth root, so intuitively it should be clear anyway. Alright, and then we need to know two key theorems that we proved earlier. Is that if you have a power series, then first of all it has a radius of convergence, which is given by how? Which formula? So the radius of convergence is 1 upon lim sup of this quantity, where we have the convention that 1 upon 0 is infinity and 1 upon infinity is 0. So this is the radius of convergence of any given power series, and we showed that any power series can be thought of as a genuine function. Right now this is just a formal expression, but if you restrict it to this interval, then it's a genuine function. If you take an x from this interval and feed it here, you get a real number out of it because the series will converge. Moreover, the power series will converge uniformly in any truncation of the interval of convergence, or the disk of convergence as we call it. So this is what we proved. And then few lectures earlier, we proved a very nice theorem about a given sequence of differentiable functions converging to some limit. How do the derivatives of the participants behave with respect to the derivative of the limit? So under some hypothesis, a very nice behavior was observed. So assume that the given sequence of functions was convergent at one, or was a sequence such that if you feed one particular value to it, you get a convergent sequence. Okay, so this sequence of functions, we are not assuming that this is a pointwise convergent sequence of functions or anything. We are just assuming these are differentiable functions, and that there is a point in the domain such that the corresponding sequence of real numbers is a convergent sequence. Alright, and now if you further assume that the derivatives of these functions form a uniformly convergent sequence, then the original sequence of functions also converges uniformly, and the derivative of the limiting function is the limit of the derivatives. So that's what has been written here. So we saw all these things before, and today we will use them. So here is the main theorem, or at least a main theorem of the entire lecture series, if you will. Fix a power series. Let R be its radius of convergence, and as we recall, this is nothing but 1 upon lim sup right? That's the radius of convergence. And once we have a power series, we can define a function on the disk of convergence as that. Sounds like a bummer because we have just repeated the same expression here, but it's just that this we treat as a formal object with nothing to do with real numbers in a certain sense. But in the disk of convergence, it takes a real number as an input and outputs a real number. So we have just defined a function using the power series, and then what we want to say is, first of all, we would like to ask, is this a differentiable function? And how can we compute its derivatives? So the conclusion is that it is a differentiable function, and its derivative can be just computed by differentiating the power series term by term. So the derivative of this term is that term. So the derivatives of power series can be computed term by term, so to say. Right? So that's very nice. So it is actually as nice as things get. There is no technicality here. You have a power series. It is a differentiable function, first of all, in its disk of convergence, and since it is differentiable in its disk of convergence, you can differentiate it, and the derivative just can be computed by writing the power series of the term by term differentiated thing, as nice as things can get. Okay. So how do we prove this? Well, let's write down what we want to do. What we really want to do is the following. Define Fn as the sequence of partial sums of the given partial of the given power series. Right? Fn is nothing but the nth partial sum of this given power series. And we've already defined f in the question itself. So what we really want to do is the following. Or even before that, what we know is, we know Fn converges to f pointwise. In fact, we know something more. We know that Fn converges to f uniformly once you truncate this thing a little bit. Let me not write that, but we know this. We just want to say that Fn prime converges to f prime. Well, before even saying that, we want to show that this is differentiable, and that if you differentiate these guys, they also limit to something. And what is that something? That something is the derivative of f. This is exactly what the question is, or what the theorem is. So naturally, we would like to invoke the theorem about uniform convergence and differentiation. There is one theorem that we know which talks about the derivative of the limit being equal to the limit of the derivatives. So we would like to invoke that, and the rest of the proofs just uses or is motivated by that theorem, if you will. Or perhaps the correct thing to say is that that theorem was motivated by this theorem. In order to prove this theorem, you need that theorem. Okay, whatever. So here is the natural thing to do. Define, or first consider this power series. Consider the power series. Right? It is this one. And let's figure out its radius of convergence. So our claim is, the radius of convergence of this power series is also R. So R was the radius of convergence of the original power series, but we are saying that even this has the same radius of convergence. This is a very simple exercise actually, but let me at least write some details. So the point is to compute this quantity. Lim sup of what? Of the nth term here if the index was starting from 0. That's how we express the radius of convergence, right? If the index is starting from 0, you take the nth term. You have the 0th term, you have the first term, and so on. You take the nth term, take the absolute value, take the nth root, take the lim sup, and then you divide that whole thing by 1 by that whole thing. That is the radius of convergence. But I'm forgetting this part here, just to not clutter things. So the nth term here, if the index was starting from 0, would be the following, though it hardly makes any difference. Now this is simply this product. I forgot to take the nth root. Right? This lim sup. But this thing limits to 1, as we recalled in the beginning. So just to find, this is a little exercise for you that you can kind of forget about that term. So this justification is a small exercise. And further, this is equal to, again, I'm forgetting the nth root every time. And this justification is also a small exercise. All we are saying is that this n plus 1 can be replaced by an n without any difference. And therefore, since these two quantities are equal, the radii of convergence of this series is same as that of that series. So the two series have the same radii of convergence, and hence the same disk of convergence. So this is some side observation. So what is the point? Since we wanted to use our theorem about uniform convergence and differentiation, we would like to say that the derivatives of these functions, they converge uniformly. right? That's what we would like to do. What are the derivatives of these functions? The derivatives of these functions are nothing but given by this formula. Right? Fn is derivative through and through in this domain. In fact, for all real numbers, if you extend it to all real numbers, but we won't extend it to all real numbers. So Fn prime is defined on this region and is given by this formula. Right? And what does it converge to? What we just observed? We just observed that since this thing is at the very least pointwise convergent in this region, and what is its sequence of partial sums? Its sequence of partial sums is precisely these functions. Right? Whatever this function is on this region, if you just take the sequence of partial sums, you get these functions. And we know, since this is a power series convergent in this region, since this is precisely its disk of convergence, Fn primes converge pointwise to that. But pointwise convergence of Fn primes are not, that condition is insufficient for us to apply our theorem about uniform convergence and differentiation, because there we need in the hypothesis that these are actually uniformly convergent. So what do we do? Well, this is a power series. It converges pointwise in its radius of convergence, but it converges uniformly in any truncated disk of convergence. So that is what we will bring in. So therefore, the rest of the proof is precisely because of the lack of uniform convergence of this guy in the entirety of this domain. So if we truncate it a little bit, so let epsilon greater than 0, think of it as a small number. So we know by what we said earlier, I'm not going to write too many details here. So we know that this converges uniformly. This is a uniformly convergent sequence of functions, right? Make sure you get this point. This is the sequence of partial sums of this power series. And once you truncate the disk of convergence, the sequence of partial sums will converge uniformly. This is a fact about power series in general. That in fact we recalled this in the beginning. And now we can apply our theorem about uniform convergence and differentiation, provided we can find a point in this region such that this sequence, once you feed in that point, call it x0, this sequence is a convergent sequence. That was the only extra hypothesis that we need to satisfy in order to apply that theorem. Can we find such a point here? Not here, but actually here, right? Can we find such a point here? Of course we can, because 0 is one such point. If you plug in 0 to fn's, fn of 0 is just constant. Fn of 0 is a0 for all n. So that hypothesis is trivially satisfied. So what we see is, because I'm not writing everything, I'll put a ... So what we see is that this sequence of functions is differentiable. We already knew that it is differentiable. So what I'm trying to say is, this sequence of functions, this is a sequence of functions such that the derivative of the limit is the limit of the derivative. So in particular, the limit is differentiable and the derivative of the limit is the limit of the derivative, such that the limit of the derivatives, again restriction, is the derivative of the limit. But what is the limit? What is the limit of these functions? It is just f restricted to this interval. So this shows that this is the differentiable function and its derivative is the limit of these things. But this is true for each epsilon, no matter what epsilon you pick. This is true. So what we have is, again, ... This just gives us what we wanted. This is exactly what we wanted to prove. Okay, so just fill in the gaps for these two dot dot dots. Very simple to do. And make sure you get these little gaps, and that's all. So that's a very nice theorem, very useful one. Okay, and let's just look at one more theorem and then we are done. It's actually a very important result. We have a power series. It has R as its radius of convergence. We define the function f as in the previous lemma. Then this function is differentiable as many times as you want, and you can compute the kth derivative just by differentiating each term k times and then summing up and forming this new power series. And this is just a repeated application of the previous one. If you differentiate it one time, so we already showed that it is at least one times differentiable, and this derivative is also given by a power series which has the same radius of convergence as the original power series. So you can keep applying the previous theorem, and if you do that, you will get this result. Right? So this again here, everything here is an exercise. It's a very, very simple exercise. So that's it. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.